Well, it's great to be here. This is a wonderful conference. I'm very much enjoying it, great diversity of contributions. I want to talk to you a bit about the Alan Turing Institute, partly about the Institute itself, which is very new, and partly about a program in data-centric engineering, which has been very generously funded by the Lloyd's Register Foundation. And actually, the foundation were really the first to put their hands up and say and see what the Alan Turing Institute was trying to do and to come alongside and support us. And of course, they were very much fired up by the review that they did. There are copies of this outside on the tables. Excellent review they did on the potential of big data, and that it was kind of obvious to them, I think, to come and align with the Alan Turing Institute, which is also about big data and data analytics. It began when George Osborne, as a result of a letter which was routed through the Prime Minister a little earlier, finally announced that the Alan Turing Institute would be happening, and that it's all about big data, yes, but also about the algorithms that go with big data. Here we are in on the British Library site at the top there. We have rather beautiful premises which have just been made ready. We've kind of spent the year getting ready, hiring people, connecting with partners, and this has been a wonderful week or two, the last couple of weeks, because people have actually arrived, and now we have about 150 altogether. So, instead of talking about what this institute would be like in a vacuum, we can now, I had tea yesterday with a bunch of research fellows, and the day before that with a bunch of research students. It really is wonderful that it's in operation. It begins with big data, which, of course, was one of the 8 great technologies that was talked about this morning. And, it's commonplace for us now that these kinds of more alive than dead type of statistics about how much data there is in the world. And it's a little daunting, I suppose. And then, of course, you have to spend money, as government did, on providing for all that data. Where is it all going to live? What is going to be used to compute it? And so a lot of investment went in from government as a result of the 8 great technologies in housing that data and providing for it. But in a way, owning data is not yet an asset. It's actually a cost, and it only becomes an asset when you can really get some value out of it. So Mike Lynch, famous founder of autonomy, has one way of looking at this, which is thinking about all the information that comes into businesses, into your enterprise, which is not really in a suitable form for computing. It's in a very disorganized form. A lot of it will be free text. And so there's a tremendous amount of interpretation to do before one can really begin to get the value. And a vice president from Gartner, the analysts, puts it like this, that big data is an asset for companies, but it's only when you turn that data into actions and decisions that it really is a benefit and can make a profit for your organization. So we're very much focused on analyzing the data and the algorithms that get value out of them. That's what the Institute is all about, to research those algorithms, but also to turn them into reality by applying them to things that matter. So that's what the Institute is all about, exploring the potential of data science. Data science is a new subject which is just evolving. I mean, there's a lot of healthy skepticism about it. Is it just a rebadging of statistics? I don't think so. I'm with David Donahoe, the scientist from Stanford, who's written very eloquently about this, that at the core of data science is a kind of collision between statistics and computer science. Statisticians know all about how to analyze data. They also know about programming. They've invented several languages like R and S for themselves. But computer science thinks a lot about scale, about the complexity of algorithms, about scaling them up, about running algorithms in a distributed way across many machines in a data center. And so I think this sort of collision between disciplines is at the core of what we're trying to do, and I think it's quite fascinating. Here we are. This is the simulated institute, which we had to live with for a long time, but now we have a real institute. But the thing I wanted to point out is that it's one long space, about 3 cricket pitches long, and I like to think of it as a kind of a pipeline, not too literally perhaps, but we're a sort of, as it says, we're an institute without disciplinary boundaries. We don't have a statistics department and a computer science department and a mathematics department, but we have all of these people mixed into this space, all working together. And I think conceptually, it is a kind of a pipeline. So as I said, the core of data science seems to be this collision between statistics and computer science. But we also have mathematicians, because we have a feeling that people who think in the abstract about geometry and topology might think of some quite new ways of looking at data and processing it. So we really want to allow this kind of a strong component of this kind of exploratory work. We've had a wonderful, an eloquent speech on serendipity from Andre Geim earlier on, that often the things you discover are not the things that you were looking for, and even on a kind of prosaic personal level, I don't know if you have this experience, but I think one is often most productive when you're being naughty and you're working on something that you know something else has a deadline and you should be working on the other thing, but if you work on this thing you shouldn't work on, it's often very, very productive. So we have the mathematicians thinking of new ideas, and by their nature, they are theoreticians. We have applied mathematicians, actually, who work on things like optimization and signal processing. We also have the pure mathematicians doing the topology and geometry, and the hope is that they will feed in to the thinking of statisticians and computer scientists who will also be talking together, and that we have this kind of stream of this bucket brigade of different kinds of people getting ever more practical until it sort of pops out at the output end with software engineering. And so we're hiring software engineers, which is not something which is actually that easy to do in universities. Universities are getting around to doing this and seeing the value of it. It's quite hard culturally for them to do it. And so we've started off from the very beginning hiring what is at the moment a small team of software engineers, but my hope is that this will be so productive and so obvious that this is the way to get ideas out into the world that my board will allow me to hire more engineers, and that I think is very exciting. Now, we also have the social scientists, and that's also very important. The social science community was very clear at the beginning when we were establishing the institute that they wanted to be included, and they were worried that we wouldn't include them. And so I'm used in my previous role in Microsoft to paying attention to social scientists, designers. I think it's terribly important to have these disciplines so that the others, the three at the bottom, don't collapse onto their own geekdom. I mean, it would be easy to do that and tempting, but the social scientists will keep us connected with the real world. And I think the flow from social science to the technology is kind of two-way. There's social scientists understanding the nature of problems and the nature of users. There are the users up at the top, and keeping us technologists real about how users really behave, what matters to them, how they will respond to technology. But then there's also, I think, a very interesting flow the other way, which is that the new methodologies in data science, which are being invented here, are really having a big impact on social science and the way social science experimentation is being done. And I guess theoretical work on networks and on network algorithms is a great example of how social science is really being turned around. So here's what our roadmap looks like at the moment. We are, as I say, we've spent the year building ourselves up, hiring people, getting ourselves together. We've got about 150 people on our books at this point. And there wasn't time to kind of think about our strategic priorities. Might have taken us best part of a year to do that, and then go out and hire the people. We had to kind of do it all at once. And so this is as far as we've got, and I think this will be a living diagram that will evolve over time. You see, we are looking at 6 different areas of challenge, which are the verticals there, and 4 different kind of intellectual streams that are feeding into those challenges, all the way from the mathematical ones that I mentioned, all the way through to the social science ones, understanding human behavior. And in the verticals, of course, the one that is absolutely tied into Lloyd's Register Foundation, and by the way, the verticals in many cases are linked up with partners. The Lloyd's Register Foundation vertical, of course, is engineering more than anything else. And this is going to be a great adventure that we're going on together. I don't quite know why I put this slide in, but just to say, in order to support all of this, of course, we do need first-class computing, and Well, it was quite a nice announcement last week, which is that we know that Intel already have come alongside and are going to provide us with parallel computing facilities. But last week, Microsoft also announced that they were going to give us $5 million worth, which is nearly £5 million now, isn't it, of Azure cloud computing, which is a fantastic facility for us to do this, to do research at scale. So now to zoom in on the program with the Lloyd's Register Foundation. They've given us very generously 10 million over a 5-year period to work on data-centric engineering, in some sense to realize some of the vision in this report, which, amongst other things, recognizes the key importance of data analytics, one of its key recommendations. And so we've begun to develop the program. And this month, we've put the first piece of the program in place, and it has 3 components. The first theme is on resilient networks, and I'll come back to this in a moment. But this is, I suppose, responding to, thinking back to the Willett's talk this morning, and he was doing on a country scale what we're trying to do on the institute scale, which is to think about what the people we have are actually good at, and to try to build something out of that. You can make a very high-level strategic decision to do something and then discover you don't really have the talents, on your staff to do it. So there's a kind of delicate balancing act here between the top-down and the bottom-up, which we're trying to do. And one of the things that is clear is that we have people both at the applications end and at the kind of mathematical end who are thinking deeply about graphs and networks and how one can compute in them. And in our kind of everyday built environment, this boils down to things like flows of people, flows of water, flows of electricity, networks of vehicles, charging, networks of communications, including under extreme conditions where communication networks may have broken down, and it may be important, let's say in a disaster scenario, to work out how to repair that network as efficiently as possible and to get the computational tools that will help to do that, all key parts of the kind of robustness of our built environment. The second thing we're doing is a kind of pilot study in anomaly detection, and I'll come back to this again in a moment, but we can think of all different kinds of safety-critical environments where one needs to know about anomalies, some on slow time scales, some on short time scales. So, for example, turbines are a great example. Siemens, we've talked to quite a bit, are very interested in turbines, and they collect data over on the scale of a day, and they're listening hard to see whether a power-generating turbine might be giving away some sign of unreliability, something that needs attending to with early maintenance. And this is a beautiful theoretical problem as well, because you've heard a lot about machine learning, and with machine learning, the classic thing is that you're trying to distinguish between 2 different classes of things, maybe dogs and cats, shall we say, and I'm a vision person after all, and you've got lots of examples of both. But with anomaly detection, the interesting thing is you only have a lot of examples of the normal condition. You very rarely see the abnormals because they are abnormal, they're unusual. And so you've got to do this kind of one-sided classification, which involves also temporal processing. So that's a very challenging problem. And then we have another kind of incipient program in automating analytics. This is really the fundamentals of doing data science, which feeds into many applications, including the safety-critical ones. So I just want to finish by showing you a few of the things that the scientists who are coming from our 5 partner universities, which, by the way, are Oxford, Cambridge, UCL, Warwick, and Edinburgh, along with EPSRC as a founding partner. These people are coming into the institute at all levels, senior, mid-career, and junior. And here's a study from Cambridge, which I rather like, which is all about trying to analyze traffic. Now, the sensible way to analyze traffic in an urban environment would be to install sensors. It can be done, but it's rather expensive, especially, connecting them up and all the problems that Jeremy was telling us about in the last talk. So Richard Gibbons and his colleagues in Cambridge had a rather cheeky idea, which is to use the fact that the buses have GPS on them and to use the buses as proxies for the motion of the buses as proxies for the motion of the traffic. Now, this is, has obvious value and obvious pitfalls. And statisticians and machine learning people love that. There's nothing more delicious than taking data which was designed for one purpose and repurposing it for something else where there are defects and flaws, because then one can use the power of statistical modeling to patch up and repair those flaws. And the result was that they were able to analyze some interesting anomalous events in the traffic network. For example, an accident on a particular day, 2010, I think it was, around Cambridge. And this heat map here is showing the flow of traffic on an ordinary day. But on this particular day, you see all that red in the center, where the knock-on effect of one accident has clogged up the network. And the accident actually, there it is at the top left on the ring road. But the knock-on effect over the kind of rush hour period was quite extensive, and they were able to sort of use the bus data as proxy for analysing that. Some of our insights, I think, will come from quite strange areas. Here's one of our Oxford scientists, Steve Roberts, who's been studying pulsars with colleagues in astronomy, and what you see there is a series of profiles at the top left of typical pulsar pulsars, but then the last two have got anomalies in them, but these anomalies are not, what you're seeing there is not the result of one observation, but a kind of statistical accrual over many observations, because this is extremely noisy data. And the plot at the bottom is about the rate of slowing down of the pulsar, and you see a little surge there around 2005 in the rate at which the pulsars are slowing down, which indicates an astronomical event, actually something falling in, a body, asteroid-like body falling into the pulsar. And, on the face of it, this doesn't have anything to do with engineering, but on the other hand, we celebrate the diversity of people coming in with experience of different disciplines, crossing disciplines with their insights, and I think that's one of the things that's going to be particularly rich. Here's another example of that kind of serendipity. We have people working on optimization, on using GPUs, graphics processor units that are really designed for gaming to speed up optimization. It's very important in machine learning, which is at the foundations of data science. But here they're using it rather interestingly to design structures. And this is the spending 20 seconds, 200 seconds, and 20,000 seconds on optimizing the structure of a bridge where even at the outset the topology isn't known, but the bridge is kind of pulled together by optimization and using the GPU. The GPU, with ingenious use, allows speed-ups of times 100, and we hope to use those kinds of insights in core data analytics as well. Well, I think I'm probably about out of time, wouldn't you say? And so I think I'll stop at that point here. I'll leave the slide with our strategic priorities on it. And Lloyd's Register, of course, is coupled into all of the horizontals there in methodology. Also, the engineering stream is absolutely theirs. I think there'll be good couplings as well into technology, which is all about computer architectures that are specialized for data science, and into security, the third stream. And we're very excited about working with the foundation as we go forward. Thanks.
Thank you, Andrew. Okay. I hate to do this, but to say maybe just one question, if there's one question in the audience.
In terms of the big data versus surpass modeling technique, actually we are talking surpass. We are talking about big data. It is obvious that big data is still insufficient in quantity to analyze the reality perfectly. Therefore, it is said that the surpass modeling technique is much better than big data modeling technique. What is your view on this?
Well, I mean, I don't see sparse modeling and big data exactly as alternatives. I mean, sparse modeling is a powerful way of getting the structure out of certain kinds of big data. For example, I guess the best known application may be in recommender systems, where you have 1 million items that you're selling and 100 million users, and potentially you've got you know, what was that, 10 to the 14 sort of entries in that matrix, and so that's obviously too big. But by exploiting the sparsity that's inherent in that system and imposing it on the matrix, you get insight. So I would say sparse modeling is a powerful technique for handling big data.
Okay. Super, thank you so much, Andrew.
Thanks. Yeah.
Okay.